Alrighty, so today we're going to be having a look at the turning point form of the quadratic equation. And what you'll notice is that it's got a constant out the front, like our previous form did, but it's also got these two elements here, which look a lot like our horizontal and vertical translations. And indeed, that's exactly what they do. We call it the turning point because the turning point's the most easy part to map. If we have the turning point of a quadratic here, and we translate it B units and C units, B units to the right, and then C units up, well, that's just where the new turning point's going to be. So we call it turning point because B and C is the location of our turning point, which makes it really easy to sketch quickly. So let's go through and have a look. Now just be mindful, B has the negative, C does not. So B, whatever the sign of B is, you're going to switch, whereas whatever the sign of C is, you will not switch. So if I have the function y is equal to x minus 3 squared plus 5, well, I can immediately read off that it's going to be at the point 3, 5. That's where the turning point. So the turning point is going to be at 3, 5. And since there's no other dilations or reflections happening, I don't have to change the shape. So let's quickly sketch it. So 0.35, 3 across, 5 up, is here, and then it's just going to be the usual quadratic shape from there. And that is y is equal to x minus 3 squared plus 5. Now, obviously, you could have a think about whether there'd be any x-intercepts or any y-intercepts. There's definitely going to be a y-intercept that's going to happen somewhere up this way, but it looks like it's never going to touch the x-axis, and that's indeed correct. So it's a good thing to just have a practice of all of those skills we've been working on. Alrighty, so I know what the turning point is, so the other piece of information is, are there any x-intercepts? And we could try and solve for it if we wanted to, but in this case, I'm not going to worry about that just yet, and I'm just going to say that there are no x-intercepts, which does happen with quadratics, because if you move it up, or you move it down and you reflect it, then you're not going to get yourself any x-intercepts. It's never going to hit the x-axis over here. But it is always going to hit the y-intercept, and the y-intercept happens when x equals 0, so we can just sub that in, and we get y is equal to 0 minus 3 squared plus 5. 0 minus 3 is 9. Sorry, negative 9 squared. Sorry. 0 minus 3 is negative 3 squared. 9 plus 5 is 14. And so we're going to get the y-intercept at 0, 14. Axis of symmetry is going to be, well, x equals 3. We've already talked about the turning point. Since it's in turning point form, we can just read the turning point straight out of the graph. The last thing we can talk about is domain and range. So domain, we haven't put a restricted domain on it, so it's just going to be x's in double R, no restrictions. However, for the range, as per usual, quadratics never get full range because of the way that they're positioned. There's always going to be some restriction on them. And in this case, it's going to be y is in the set from 3 up to infinity. Or you can write that as y must be greater or equal to 3. Either using the interval notation or the inequality notation. It doesn't matter which one you use. Alrighty, so there's a little bit on that. Let's have a look at one more and then we'll move on. Alrighty, here we have it, some much needed complication. So first of all, let's just remind ourselves what the negative mean. It means that we're going to be having a concave down shape. Okay, so really important to just keep that in mind is that as soon as you see that negative out the front, the shape that we're going to be getting is going to be concave down. Now we can just read off these 2 points. Remember, we're switching the sign of the x point, and that's going to give us our turning point. So that means our turning point is going to be -3, -5, and it's going to be concave down. And now we're good to sketch. So don't need that much information. It's not been dilated, so it's going to be the classic quadratic shape, but we're going to need a bit more negative axes space, not that much negative axes space. And we've got -3, -5 for the turning point. And since it's concave down, it's going to look like so. Once again, we found another example in which there's not going to be any x-intercepts, but there will be a y-intercept as per usual. So no x-intercept. Y-int is when x equals 0. And we can work that out quickly. So we're going to get y is equal to -0 plus 3 squared minus 5. 3 squared is 9, -9 minus -14. No x-intercept, y-intercept, axes of symmetry is x is equal to -3. Domain, no restriction, so x in double R. Range, there is the restriction. In this case, the upper bound is -5 and the lower bound is -infinity. Or you can write that as x must be smaller than, y must be smaller than or equal to -5. I'm just going to check. No, I did write it correctly before. Alrighty, so there we are. Domain, range, concave down, turning point, x-intercepts, none, y-intercept. Well, I didn't write the coordinate of the y-intercept, so 0, -14 for the y-intercept. And the axes of symmetry is x equals -3. So that just gives us a little bit of a picture on how to quickly sketch turning point form graphs. Really, really quick, really, really easy.